In this video, I will show you how you can work with an ideal gas that goes through a cycle. Now, what I mean by a cycle, I have mentioned that a state of an ideal gas system can be represented by a dot on the PV diagram. So I have state 1 here, one dot, state 2 here, another dot. I have mentioned that a process is with which the ideal gas goes from state 1 to state 2, from this pressure and volume to that pressure and volume. And what I mean by a cycle is the following. If I add one more state, maybe a little bit more to the right. So if I add one more state here, then a cycle means that the ideal gas goes from there to there. So I'm adding one state 3. I'm adding one process, the process with which the gas goes from state 2 to state 3, and one more process, with which the gas goes from state 3 to state 1. So let's mark this. Okay, this is state 1, this here is state 2, this here is state 3, this is state 3, and this is, okay, let's fix the mistake. So as I said, this is state 3, this here is a process, and this here is also another process. So my ideal gas will start from state 1, go through a process, reach state 2, go through another process, reach state 3, go through the last process, and come back at the same point. This is what a cycle is. Now, different things happen in these 3 different processes. Okay, I have mentioned before, I'm using an isothermal process to go from 1 to 2. Now, because the gas goes from state 2 to state 3 with a constant pressure, that means I'm using an isobaric process here. And remember, an isobaric process is shown on the PV diagram as a horizontal line. And because the gas goes from state 3 back to state 1, keeping the volume constant, this is an isochoric process, this over here. So the theory is different for these 3 processes. That's what I have summarized here. And I have already shown you how to work with state 1, how to work with state 2, how to use the theory for the process when the gas goes from state 1 to state 2. Now, this is what I'm going to do. This is what I'm going to show you to do. I'm going to work on state 3 because I know state 1, I know state 2. I need to find everything I can about state 3. And I will also work on the isobaric process that the system used to go from state 2 to state 3. But first, let's see what we can do about state 3. For state 3, I know what the volume is. Okay, it is here, the same as the state 1 volume. I don't know. I do. I know the pressure. This is the pressure in state 3 is the same as the pressure in state 2, and I know the number of moles. So I know this. I know this. I know the number of moles. I know the gas constant, of course. I don't know the temperature in state 3. So I'm gonna use the ideal gas law to find the pressure in state 3. Let's do that. So for state 3, the pressure of state 3 is the same as the pressure of state 2. I'm gonna go back and look at the number, what that number is. And I know the volume of state 3 is the same as the volume of state 1. Okay, let's go back and find the numbers. I don't think I used any numbers here. So the pressure at 2 is 1.9 divided by 2, 10 to the 7. Pascals. And let's find volume 3, which is the same as volume 1. So I'm looking for, I found the volume to be 5 times 10 to minus 4. Let's use 2. Two significant digits, 5 times 10 to minus 4 meters cubed. And the theory is for state 3, P3, V3 equals N R. The temperature for state 3, remember I know everything but the temperature, so I can say the temperature in state 3 is P3 V3 and R, and I know all of these numbers. P3, so 1.9 divided by 2, 10 to the 7, 5.0 times 10 to minus 4, 3 moles times 8.31. So I have everything here. I can find the temperature of state 3. Now, the way that I like to do these calculations, I can give you a hint. It may make your life a little bit easier. I like to take out the powers of 10 and do the calculations with the rest of the numbers. So what I did 1.9 divided by 2 times 5 divided by 3 and 8.31. And this gave me 0.19. Now I'm going to take care of the powers of 10. I have 10 to the 7, 10 to minus 4. So this will give me 10 to the power of 3. And this means that final temperature, the temperature in state 3 is 190 degrees Kelvin. Okay, that's how I prefer to do the calculations. Now, I found everything. Now I know everything about state 3. I'm done with state 3. And if I go back to, let's see. So here is my diagram. I know everything about state 1, I know everything about state 2, I know everything about state 3. So I have all the information about the 3 states. I did the work for the process going from 1 to 2. Now I need to work with the process going from 2 to 3. And as I said, here the pressure stays constant. So I have an isobaric process. In this case, the work that the gas does is the pressure times the change in the volume. And I'm gonna use this expression to find the work that the gas does, and I will also use this expression to find Q. So let's go. Now I'm dealing with the process going from state 2 to state 3, which is an isobaric process, so the change in the pressure is 0. The work that the gas does is pressure times the change in volume. Now, remember, the process going from 2 to 3 has a constant pressure, so whether you use P3 or P2, it doesn't matter, they are the same number. If you remember here, P3 and P2 are the same. Now, the change in volume, okay? I go from the initial state of 2 to the final state of 3. So my final is the volume of 3 and the initial is the volume of 2. Now I need to use the numbers. 1.9 divided by 2 times 10 to the 7. And I have V3. What is V3? Is 5 times 10 to minus 4. And let's see, I think V2, if I remember correctly, is 2 times this. So we have 10 times 10 to minus 4. And let's see, let's move on. The work done by the gas, 1.9 divided by 2. If I combine the powers of 10, this will give me 10 to the 3. And then I have 5 minus 10. That will give me a minus 5. And minus 5 divided by 2, we have 2.5. Will give me a minus 4.8 times 10 to the 3, or minus 4,800 joules. Now I want to remind you, this is the work that the gas does on the surroundings. If I want, and I do want at some point, the work that the surroundings do on the system, I need to use a minus sign, so minus the minus will become plus 4,800 joules. I found the work that the surroundings do on the system. Now I need to go, let's go back in the theory. I finished with the work done for this process. Isobaric, I did this calculation. Now I'm gonna do this calculation to find Q and Cp delta T. So Q and Cp delta T. I know what N is. Cp is just the constant. Now the final temperature minus the initial temperature. Remember, final is 3, initial is 2. So I need T3 minus T2. And I remember the number of moles is 3. Cp is 20.8 for an ideal monatomic gas. The final temperature is 190. The temperature, if I remember correctly, T2 is 373. And this will give me minus 11,000 joules. Okay, this is Q. And to finish this, I will find, I'm not sure if I need it. Probably I don't need it, but I'm gonna find it anyway. I know from energy conservation, the change in the thermal energy is equal to W plus Q. Now for W, I have the work. I need to use the work that the surroundings do on the system. So this is the 4,800. Q, I already found it, minus 11,000 joules. And this means the change in the thermal energy for the gas going through this process is minus 6,200 joules. Okay, and now I have everything. I have W, I have Q, and I have the change in the thermal energy. So whatever I need for this process, I can find it. Now, to remind you, at this point, I know everything about states 1, 2, 3. Let's go back to our PV diagram. I know everything about state 1, state 2, and state 3. I did all the work for the process. I did all of the work for this process. The last thing I need to work on is the process, the isochoric process. Here is the theory. Going from state 3 to state 1. So for an isochoric process, I know that W is 0. Let's add a new board. So the last thing I need to do is work on the process where the gas goes from 3 to 1. And that is an isochoric process. So the delta V, which is equal to V1 minus V3 is 0. Because the change in the volume is 0, this means that the work that the surroundings do on the system is 0. And from the energy conservation principle, W plus Q, since I know that W is 0, the change in the thermal energy is just equal to Q. Now I will show you how I can move on. I will go, I'm gonna show you on this board about the change in the thermal energy. I mentioned at the beginning in a different video that the change in thermal energy is the number of atoms times 3 over 2 K delta T. Alright, so my program crashed as I was recording this. Maybe it became overwhelmed with all the stuff. So as I was mentioning, N times K, the number of atoms, Boltzmann's constant. If you take a look here at the two expressions of the ideal gas law, N times K and number of moles times the gas constant, those two are equal to each other. So I wrote N times K as little n times R, and then I can go back to my calculations. And I did, so as I said, I was working on this while the program crashed. The change in the thermal energy, I can calculate as N 3/2 R delta T, and I use the numbers. T1, state 1 is the final state, state 3 is the initial state. So I have 373 minus 190, and if I do these calculations, I will find 6,800 joules. And since delta E thermal and Q are the same, are equal to each other, it means that Q for this process is also 6,800 joules. And now I have everything for the process going from state 3 to state 1. So I can go back, going back here. Now I have everything for states 1, 2, 3 for this process and this process and this process. And now I have everything about the cycle that this ideal gas is doing. I have all the information that I could possibly have about this ideal gas.